Mr. Manuel Ruiz has not been able to connect. He just dropped me an email, so we will play the video. But Pascal, maybe you can just introduce him shortly because I also haven't received a bio from him. Could you do that? Wait a minute, I have to switch on your microphone. No, we can't hear you, unfortunately. May I ask my co-host to enable Pascal's microphone? Unfortunately, I can't.
Yes, it should be fine now.
Yeah,
no.
now it's fine. Okay, please.
Okay.
Just briefly introduce him, please, or yourself, maybe.
I'm looking, yes. Okay. So Manuel Ruiz is a research engineer at the R&D department of RTE. He has a PhD in mathematical programming and works as an expert in optimization, decision-making, and operational research at RTE, including economical dispatch, AC and DC optimal power flow, exploitation of the grid. He has a strong knowledge on linear and non-linear programming, optimization problem with complex variables, robust optimization modeling, and algorithm methodology used to solve them.
Okay, thank you very much. And you're also ready to answer questions then after the presentation.
Okay.
Okay, thank you. So then, can we have the video, please?
Welcome, everybody. My name is Manuel Ruiz. I'm working at RTE. And I thank you all for coming to my presentation about good optimization-based outage maintenance planning. RTE is a French transmission system operator. Our main missions are to operate, maintaining, and developing the transmission system of France. We also have to assess the security of energy supply in real time. This is mainly the adequation between production and demand. We also participate to the market design of the European market. RTE owns and exploits the most complex network in Europe. We have more than 100,000 kilometers of transmission lines. We have a network with more than 2,600 of substations. In winter, the demand peak can exceed 100 gigawatts. And in the figure at the bottom, you can see that RTE is fully connected to producers, consumers, and also other countries interconnected with France. There is a paradox between two of our missions. We have to maintain the grid. This requires switching offline and weakens the network. And we have also to assess the security of energy supply, and this is more difficult with a weaker network. So the question is, how can we operate the grid in a way that both maintenance and security assessments are optimized together? Moreover, with the energy transition, operating the grid is more and more complicated due to the integration of renewable energy. So this is a big challenge for RTE that we call grid optimization-based outage maintenance planning. And there are two key points in this challenge. Being able to maintain the network of today in short or mid-term planning, but also to assess if maintenance planning will still be possible in decades and long-term planning in network development. We designed a three-step approach in order to deal with this problem. In the first step, simulations of what occurs if one intervention is planned at each time step of the planning horizon are made using tailor-made RTE's security assessment tool. Basically, it simulates the N-1 rule, which is the evaluation of the redispatching costs following the loss of one transmission line or one production unit. Several realizations are studied for each time step and each intervention. The step 2 is dedicated to optimization of outage planning, knowing the risk-value distribution of each intervention. And finally, we validate and assess the robustness of the planning. And Today's topic is how can we optimize the maintenance planning knowing the risk distribution. Before showing the mathematical formulation of the problem, we will illustrate it on a small example. Let's imagine we have time horizon H, which is composed of 3 time steps. We have 3 interventions to be planned, 1 result, and security assessments during step 1 are made using 3 scenarios. Moreover, we know that we cannot plan I2 and I3 at the same time because they are too close in the network. So what we call a feasible solution is a solution that is feasible regarding resource constraint at each time step, basically lower and upper bounds. We also need that exclusion constraint is satisfied, and this is the case because I2 and I3 are not planned at the same time. And we also need that intervention are not split and are finished at the end of the time horizon. The question is now, what is the cost of this solution? Remember that we have risk distributions for each intervention at each time step. We define the optimization criterion as the sum of 2 terms. The first one is the mean risk value, which is basically the mean of the sum of risk values of planned intervention. The second one is the expected excess, that is the positive difference between the quantile 95% and the average risk value. And on this small example, with coefficient alpha used in the ponderation between the 2 objectives, the score, the cost of the solution I presented to you is 9. So, okay, this is a very, very simple example. If we have a look at realistic risk distribution, it is more like this. The risk is expressed in euros in order to allow outage consequence comparisons. Basically, we can have hundreds of realizations for each time step. So computing the quantile can be very hard. And so the planning optimization is also very hard. And I recall you that a strong assumption is that the distribution of a time step is the sum of distribution related to interventions that are planned at this time step. And this is why we need a third step in our methodology to compute the final risk distribution without the linear assumption. So now let's have a look at the mathematical formulation of our problem. So again, given the risk values are an input of this optimization problem, the goal is to find an optimal planning regarding a risk-based objective. Well, we have constraints. The planning must be consistent with all task-related realities, such as resource constraints. So we have lower and upper bound on resource consumptions. The planning horizon is always a year, and it can be a year discretized day by day or week by week. Intervention have to start at the beginning of periods and cannot be split or cannot be ongoing at the end of the time horizon. I already talked about resource constraints, and there are also exclusion constraints for some intervention in order to take into account outage proximities. Now the mathematical formulation of the objective function. Again, when an intervention is being performed, the considered line have to be disconnected, and this is causing the electricity network to be weakened, and so security assessment is more expensive. As an input, RTE already conducted simulations for several scenarios and several time steps. So we have all these risk distribution of planning and intervention at each time step. What we can do is to compute the average risk value at a time at the average of the sum of distribution for each intervention plane at that time. And what we also define is the excess, the positive difference between some quantile, can be 95 or 80 or 90% quantile, and the average risk value at this time. And the criterion we try to minimize is then a sum with a coefficient alpha between the average risk value and the excess value. So what you can see here is that we have in the objective function a lot of term, the excess term, defined using quantile. And we didn't find any suitable algorithm or optimization-based algorithm to solve this problem. That's why we propose as the subject of the Euro Challenge 2020. The challenge was announced in February 2020 at the Roi d'Ef Congress in Montpellier. It really began in March, where subject, rule, checker, and first set of instances were published. We had an optional sprint that ended at the beginning of June. We will publish the results by the end of June. The deadline of registration and the end of the qualification phase is the end of year 2020. Announcement of qualification results will be made at WADEF 2021 Congress in February 2021. The deadline for submitting final program computational table results and extended abstract is in June 2021, and final results will be announced in the Euro Conference 2021. There is also a scientific prize which will be announced in February 2022. Here are the materials that will be available during the competition. We will propose 3 datasets, and 2 runs will be made for each, a short one and a longer one. A checker will be available. It's a Python code used to assess the feasibility and compute the cost of a solution. And you have here the list of all prices for each category. For example, we have a price for a junior team, a price for open source with accepted third dependency team, and also a price for scientific contribution to and a theoretical approach for optimization problem with quantile in the objective function. So, as a conclusion, we presented the grid operation-based outage maintenance planning, which consists in planning outage maintenance while assessing the security of supply in short, mid, and long-term studies. We presented a 3-step approach, which is based on simulations made by dedicated TSO tools, which is used in real time, planning optimization, and last step, which consists in validation with robustness assessment. The planning optimization step is the topic of the WADEF Euro Challenge 2020. You can learn more about this challenge or register yourself to candidate following this link. Thank you for your attention, and I will be happy to answer your question.
Okay, so thank you very much for the presentation. I see one question from Keith Bell. Pascal, can you read that in the Q&A box so that I don't need to read it again?
Okay, so I read the question.
Okay.
Okay. The question from Keith Bell. An interesting seasonality on slide 9, which is the slide with the realistic distribution. I'm not sure if week 1 is at the start of January. Yes, it is. If it is, the figure seems to confirm that we have always assumed that, especially in Europe, it is best to take maintenance outages in the summer. However, some TSOs are finding increasing difficulty in summer operation. For example, excess of inflexible power or lack of system services. So, has your assessment of risk been able to take into account all those kind of issues regarding voltage or regarding short circuit current? We have begin with more these questions of flow constraint. It is in order to build the risk distribution, and it is easier because we have a methodology in order to have a cost. To have congestion costs or redispatching costs for this kind of problem. For voltage problem, it will be the question for the next year because it's more difficult because it's sure that voltage problem or current circuit problem can have an impact on the planning of an outage, but we need a cost of value linked to the risk, because we need to have a balance between all the interventions we want to plan at the same moment. First, we have begin with the flow congestion problem, and we will try to have for the voltage problem or the short circuit problem to have subsidiary metrics which we'll be able to use when we have not congestion cost problem. And it's very difficult to mix in the same problem different kind of metrics which can be related because they are not on the same cost basis. So we are conscious of this issue, and we will perform further analysis in order to have this kind of realistic information in order to plan all the outages. But you have to understand also that we provide to our operator, because we have put into order this kind of first solution, we provide to the operator the possibility to act on the planning and to modify the planning and to impose some intervention for some specific problem which are not visible on the metrics.
Okay, so thank you very much for the answer. May I can ask one additional short question? If you do this sophisticated maintenance scheduling, how can you deal with unforeseen repairs due to faults which may occur in the grid?
Yeah. Yeah.
So the real life problem.
Yes. You have seen in the presentation there is a first step. The first step is in fact also designed to test the robustness of the planning to hazards, which could be resources hazards, for example, or other kind of hazards. So the question is, if I need my planning to change, will I be robust to those kind of change? Which means that you have to take care at the same moment to plan some interventions you can change and some others which are fixed for example, resources organization. So
Okay, I
we
see.
will be working on this subject also, which is a very difficult subject also.
Okay, thank you very much.